we saw that when we do a left shift, the number of bits can potentially increase. For example, here 160 became 320, which requires one extra bit to be handled. Now, previously we looked at this idea of clipping this whole thing. So, for example, in this case, we might just say, okay, let me clip the answer to 255. In this video, we'll see another way we can handle this, which is also quite interesting from a practical point of view. It's used in a lot of applications, which is to say that, okay, look, let me not drop this bit. Let me not clip the, let's say, number basis this bit. Let me instead do a circular shift, kind of what we were doing, let's say, in the Caesar cipher and so on. So the idea is that instead of dropping that bit, I will instead move it back to wherever the location is. So basically it would have gone here. Instead of that, I'll bring it to, let's say, this point. So like I said, this is a variation, not a clip, but instead we rotate. What that means is that the number of bits in the output remains the same as the number of bits in the input. In this case, for example, 8 bits. Let's take one more example. So if, let's say, I was doing a shift by 3, so in that case, basically these 3 bits would have potentially got dropped, or let's say clipped, if I was clipping the number to 8 bits. However, now I'll not, or let's say the bit would have increased by 3. Here, instead, what I'll do is that I'll bring these bits back over here, right? So this is what we are going to do. Like I said, this maintains the number of bits to the same number. And actually, it's quite interesting in practice quite useful in practice. In a lot of places, this is done. Obviously, we are enhancing the bit-by-bit project from the YByte Python curriculum available at www.ybyte.in. Now, before writing any code to do this with bitwise operators, and I think it's a great practice, by the way, to do this with bitwise operators, let us just understand how this is done, and then we will implement that in code. So the idea is very simple. Let's say we start with an 8-bit number. Of course, it doesn't have to be 8. It could be any bit of numbers, any number with any bit width. Let's say I start with 8. When I do a regular, let's say, left shift, say, for example, by 2, essentially, I'll be creating 2 zeros in the end, and the last 2 bits would have gone beyond the boundary of 8. So, the 8 ends here. The last 2 bits would have gone, let's say, here. So I'll kind of determine what these 2 bits are. Having done this, I will just kind of divide my large number into 2 parts. The one which is inside the 8-bit boundary, which is, for example, this, and the 2 bits that have gone out. I'll take these 2 bits, shift them to the right side, and I will, just do a bitwise OR to bring them, for example, like this. So you can clearly see that this will, so what I'll do is to right shift and then a bitwise OR. So that's the philosophy, that's the idea we are going to work with. Let's implement this in code so that it becomes a little bit more clear. So I get back here to my code. I define a new function called, let's say, circular left shift. So I just call it, let's say, circular shift left. And I'm going to say pass in an argument x d, the amount of shift that I want, and I also tell how many bits this number is, right? So that I know. I can, of course, I can set it to 8, but later on we'll see how we can use for other number of bits as well. So it becomes quite useful. So like I said, so this is left shift in a circular fashion. So as we just saw, right? So let's implement those steps in code. First, I just do a regular left shift. So I do that by doing x s, let's say left shift by d. So that's a regular left shift. Now remember, I want to find out the numbers that are within the 8-bit boundary or the n bits boundary, and the numbers that have gone beyond that n-bit boundary. So I do that by creating 2 masks. So I call them, let's say, mask lower is, for example, remember the first mask has to be basically all ones until n bits. So I can create that using, let's say, a combination of bitwise operators and this int function. So I just go and say, well, 0b plus, let's say, n bits times 1. Now notice these are all strings. So 1 here is a string. So I'm just saying, okay, put as many ones, 0b, for example, 1, 1, 1, 1, 1, 1, and convert this to integer, taking binary as the reference. So basically, this is a binary number that we are converting to an integer. Essentially, this, for example, will be 8 bits. For 8 bits, it will be, for example, 255, right? So something like that. A very nice usage of, let's say, bitwise operators and let's say general Python, right? Now I create one more of this. This I'll call as mask upper because these are the bits that have sort of overflown, gone beyond the 8-bit boundary. And this will be obtained by, I know there are d bits of this sort. So I just say, well, d, and everything remains the same. However, remember, this must capture those bits that have been shifted outwards. So I must go and left shift this by n bits. Think about it. these are bits which are beyond the 8-bit boundary, and hence I must left shift to create this mask. Now, having let's say created these two masks, I will first determine the bits which have gone out. I call them overflow. So I just say overflow is, well, nothing but x of s. Remember, that's the entire shifted word, regular shifted. I do a bitwise and with the mask upper. Remember, mask upper has zeros at the bottom, like in the on the right side. So mask upper, I do a bitwise and, so I get just those bits. However, I must remember shift these to the right side. So I just go and shift this by n bits. Very, very logical. I'm just putting into action the diagram that I showed you, putting that in code in a, let's say, in a step-by-step manner, right? So next, having done this, I will form my, let's say, circular shifted word by doing, well, I will first find out from the, say, say x s and let's say mask lower. Remember, these are the lower side of the, what was inside the n bits, that part of the message. And I will then, let's say, do a bitwise and with the overflow. Remember, overflow has been brought to the right side already through this shifting operation. So very logical, very sensible. And we can then look at, let's say, xcs, right? So print, let's say return, return xcs. Now, just for sake of understanding, let us put a few prints over here. So I'm going to print, for example, let's say, so print, for example, let's say mask, lower, mask, say upper, right? So that we sort of see what is going on here, right? In fact, we can also put the print, let's say overflow. So overflow. All right, so with this done, let's run this code. So when I run this code now, so I terminated the turtle window, so that's why you're seeing all these prints. But I wanted to access the terminal here. So when I, for example, run this, I want to do a circular shift of 160 by 1 and in an 8-bit system. Remember, 8 is the number of bits. So when I do this, I get the answer of 65. Let's try to reason out why this is correct and then look at also those masks. So basically what's going on is, remember this situation, I had a number 160 which was 101000000. I did a left shift, so that's why I ended up with, let's say, I did a circular left shift. This portion came here and 1 reached here, so that's why the answer is 65. But let's understand this a bit more carefully. You also notice that I'm printing the mask lower here, which is 255. That's because, remember, that's just the 8 bits all once. Mask upper is 256. That's because, again, this is just a single bit, and that's essentially 1 0 0 0 0 and so on and so forth, right? So that's 256. The overflow here is 1 because just 1 bit, and that is 1, right? So let's try this again. If I were to do, let's say, shift with 3, you notice these numbers would change. So mask lower still remains at 255. Mask upper now is 179. Now that's because the mask upper is basically this number. Remember, 3 bits on top, 8 zeros, and in binary that is 2. Now when I shift all these 3 bits down, remember my bit representation of 160 was 101 to start with. That's why my overflow is 5 here. But once I do a bitwise OR, it becomes 5, right? So very interesting. Even though I'm shifting left, but this number may end up being smaller than the original number. One thing, as you might have realized, if I were to do a left shift by the same number as the bits, in fact, I'll end up with the same exact answer. Once again, you can reason out why this is happening. But it's very logical. It's like Caesar cipher. If I do exactly the same amount of shift as the number of letters, I end up with the same letter. So same idea, but quite interesting, the implementation in the bitwise operators. So before wrapping this up, I'll remove these prints, and this function is now ready. I hope you found this interesting. In general, applying concepts, building activities is a fun way to learn programming, which is what we do at Ybyte. Look at our website, www.ybyte.in, because we learn Python programming through such fun activities. Take care. Thank you so much. Bye-bye.